Make a start. I'm not sure where our chair is, but we should start. So it's my pleasure to introduce Alex Diaz. Go for the short version of your name. Apologies. From the University of Liverpool, who's also one of the organisers of this workshop. So thank you for all your efforts so far. And Alex is going to talk about reliability-based sampling for model calibration.
Thank you very much, Catherine, and thank you very much, all of you that are here after the lunch. It's always a difficult time to listen to this kind of talk. So yes, I'm Alex Diaz. I work at the University of Liverpool for the Institute for Risk and Uncertainty, and I'm going to talk about this model calibration. It's a joint work with two of my PhDs, Alfredo Garbuno and Zitong Gong. So I'm going to concentrate on one technique for model calibration, which is called history matching. And I'm going to focus on one particular aspect of history matching, which is sampling from what we are going to call the non-implausible space. And we're going to do that using a technique borrowed from engineering reliability analysis called subset simulation. And then I will present some applications. So we all use numerical models. They are useful, they are ubiquitous. And we all know that their credibility relies on how well they are calibrated to experimental data. So what we want to do is to gather some data out there in the world, some measurements, and then learn from the parameters of our model and improve our models. So this is a challenging problem because of many reasons, but one of them is generally the cost of running these complex computer models. So if you want to calibrate a computer model, sometimes this is very impractical because you have to call this model many times, and this can be prohibitive. Now this is an important problem, and it's a problem that has to be solved, because if we don't calibrate our models, we incur in a risk of producing unreliable evidence. Yes, and for example, people who rely on these models, such as, for example, engineers, they run the risk of designing structures that are not reliable, or people who take decisions for social policies could be very well taking the wrong decisions, and that can be very costly for society, for the taxpayers. Okay, so as I said, I'm going to concentrate in history matching. So the first thing we will do is, I'm very tempted to use this piece of technology. So here, eta is a function that has its domain in a subset of the Euclidean space in d dimensions. And just to simplify things, we are going to assume that the output of this model, this function is the mapping between our inputs and our outputs. So this function is our model. So the output is univariate. Okay, so we are going to conceptualize our computer model as this mapping between inputs and outputs. So history matching, its aim is to identify a subset of this input space, and I'm going to call that subset X star, for which the output of our computer model gives an acceptable match to observed data. And I'm going to talk about how do we measure what acceptable is. So this is an iterative process. So we start by sampling the whole input space, and then we have to apply something that we are going to call an implausibility measure. This is going to impose some cutoffs, and we are going to be able to get rid or to discard subsets of the input space where it is implausible that we get a good acceptable match between observed data and our output. So what we end up with is this decreasing or nested sequence of subsets, and we end up hopefully identifying this non-implausible space, as we are going to call it. Also in the literature, people call it the non-ruled out yet space. Okay? Now, since we have to evaluate our model every time we iterate, and this is expensive, we can use an emulator. Okay? We can use a statistical approximation to the output of this model. Now, there is a subtle difference between doing history matching and doing calibration in the more traditional sense. If, for example, you're doing Bayesian calibration, you know that you are bound to obtain the posterior distribution of the parameters of your model given the observations. In this case, for history matching, it could very well be the case that this subset X star is empty. Okay, it might conclude that there is no combination of inputs that, given the model structure and given the observations, we are going to obtain any match. Okay, so it's important to have that that subtle difference in mind. So this is just a schematic of what I just said. The first thing we do is we generate an initial design. So we sample from our input space, and this initial design, we want it to be space filling, so we could be using, for example, a Latin hypercube. And those samples are then going to be evaluated with our computer model, with our simulator. And those runs are going to provide us with training data upon which we are going to build our emulator. Okay? Once we do that, we approximate the output of our complex computer model. We apply an implausibility test, and then we need to discard those subsets of the input space where there's no there's a very low probability of matching, and we sample from that non-implausible space. And I highlight this in yellow here because I'm going to concentrate on this problem, and I'm going to say why this is a challenge. Then we apply some stopping condition. If it's met, we stop, but if not, we can start again by using the samples that we generated here in the non-implausible space and evaluating them with our simulator. So in the literature, you can find that these iterations are sometimes called waves. Okay? Now, what do we use to approximate the output of our expensive computer model? We can use a number of things, but I prefer to use the Gaussian process. For those of you who are not familiar with it, a Gaussian process is just a stochastic process. If you have any choice of vectors x1 to xl, and you get this vector evaluated in this function z, and this vector has a multivariate normal distribution, then we call it a Gaussian process. And this is just a generalization of the Gaussian distribution, but this operates in a space of functions. Okay, so every realization of a Gaussian process is a function with certain characteristics. So when you are defining a Gaussian distribution, you can completely specify it with the mean and the variance. And analogously, to define a Gaussian process, you need to specify a mean function and a covariance function that we can call also a kernel. In the literature, it's called like that. And there are many characteristics that these kernels have to comply with. Some valid kernels are, for example, these two functions there. And selecting a different kernel is assuming different things about the functions that we can sample from. So, for example, if we use the first kernel, all of these are realizations of that particular Gaussian process, and this is what we call Brownian motion. Now, suppose that we use the second kernel, which is this exponential function, that is assuming that our functions are very, very smooth, so every realization is going to look, in this case, like that. And so what people do when they're using a Bayesian analysis of computer code output, they assume something about the output of this computer model. So they take a prior choice and say, I believe that the output of this computer model is very smooth, hence my prior distribution for the output is given by this Gaussian process. Okay? So if you are a Bayesian, then you need to gather some data and update that prior knowledge, that subjective information. And this is what we do. This is just a very simple cartoon. Let's suppose that there's a latent function there that is very, very expensive to evaluate. This is the input of our model, that's the output, and we can only afford to have those 6 evaluations of our output. That is objective information that we are going to use to update our subjective information. So the Gaussian process, after we do this, provides this approximation to the true output. Okay, the true output, or the output of the model. If we could run the model in all the input space, it will be given by that solid line, but the Gaussian process approximates this function using those dots there. So the Gaussian process is providing us with a complete probabilistic description, a probability distribution for the output of our computer code in all the areas of the input that we cannot afford to evaluate. So since this approximation is given by the mean of our Gaussian process, also the variance of our Gaussian process is giving us a quantification of the uncertainty that stems from the fact that we cannot afford to evaluate our inputs everywhere. Okay, so this is what we use in for history matching every time we want to approximate this output. This is what some people do. Some people do other things that I'm going to mention in a minute. Okay, so coming back to history matching, there are different types of uncertainty that we are interested in quantifying. So the first one is observational uncertainty, which is experimental error. This is subject to the precision of our instruments. We also have model discrepancy, and two of our speakers previously have spoken about this. So all models are wrong, but some are useful. There will be an inevitable difference between the reality of the true process and the outputs of our model, and this has become a very active research area. People are doing very interesting things on how to quantify this model discrepancy, which is not a trivial problem. We also have code uncertainty that stems from the cost of running our simulators, and this code uncertainty can be quantified through the variance of our Gaussian process. And we also have ensemble variability, because sometimes the computer models that we use are stochastic. For a given input, the output might change. And I'm given to understand that in certain applications, such as climate modeling, this is a useful thing to do. Okay, so schematically, what history matching is doing is, let's suppose that we have this very expensive model, and our emulator is approximating it like that. And we happen to have an observation which is given by this horizontal line, plus minus experimental error. What our task is to try to find a subset in the input space such that if we evaluate any point in that subset in our model, it will fall within that range. Okay. So in this case, of course, it's this subset is given by the union of these two intervals, and this, of course, a very simplified example. If we go to a higher dimension, this would be equivalent to sampling from these level curves. So in this case, I have 4 observations, and the task is to sample from the level curves plus minus certain, well, in this case, a certain ring around that level curve, okay? And as you can see, the non-implausible set in this case can have this disconnected, challenging geometry, okay? So it's not simple. Well, this is a simplified example, but you have to think about these problems in very high dimensions. It's not trivial to sample from this, or to generate samples from this kind of sets that have this challenging geometry. And this is the problem that I'm going to concentrate on. Okay. Right. So I also mentioned that history matching uses an implausibility measure. So this is defined by the following function. What we have here is the distance. So Z is our observations, and we have a distance between that observation and this expected value. This expected value is given by the posterior mean of our Gaussian process, so this is our approximation. But taking that distance is not enough. We have to standardize it, and we standardize using all the uncertainties that we can quantify. And I've spoken about this. This is observational uncertainty. This is code uncertainty given by the posterior variance of our Gaussian process, ensemble variability, and model discrepancy. Okay? It's a completely different problem to how are we going to estimate, for example, model discrepancy. Okay? But let's suppose for the time being that we can do that and we can assign some number to that. At each iteration, what we want to do is to find the set of inputs such that this implausibility is less or equal than certain threshold. And in the literature, you will find that they use 3, because in statistics there's this result called Purkensheim's rule that says that most of the probability mass of a unimodal distribution lies within 3 standard deviations. Okay, so this is the criterion that we are going to use. Now, in terms of sampling from that non-implausible space, there are several ways people do this in the literature nowadays. I'm aware of at least these 3 methods. The first one would be the obvious thing to do, which is just an acceptance rejection scheme. You would just generate a uniform sample in the current in the input space, and then you would test whether it is implausible or not, and you reject the ones that are implausible. Of course, this is easy to implement, but it's extremely inefficient, especially if you're sampling in high dimensions. The second term is a perturbation scheme. What you can do is, once you have some samples in your current non-implausible space, you can center a multivariate Gaussian in each one of those samples, and then draw a sample from that multivariate Gaussian, and then test whether it is implausible or not. The drawback with this approach is that you would need to tune several parameters, namely the variance of that multivariate Gaussian, because the non-implausible space shrinks very, very quickly, and in the end, it might be orders of magnitude smaller than the original input space. So you need to tune that variance. The third method I'm aware of is this evolutionary Monte Carlo method by Williamson and Vernon. This method samples uniformly from the non-implausible space, and it depends on defining a so-called implausibility ladder. So very interesting method. It's not easy to understand or to implement, but during the week I'll be talking to Daniel Williamson to understand better this method. Okay, right. So as I mentioned, this non-implausible space shrinks very, very rapidly, and it can be orders of magnitude smaller than the original input space. And so there's a natural analogy between trying to sample from a set from those characteristics when you talk to people that do reliability analysis in engineering, because they also want to sample from a particular set that is very, very small with respect to the input space. So let's put history matching aside for a minute, and let me talk to you about reliability analysis to later make the connection between the two. So the engineering reliability problem is the following. We're going to define a function, G. It also goes from RD to R, and we're going to call this a system performance function. Okay, so we have made an abstraction to represent an engineering system, for example, and this performance function is a description of everything we know about the system. It can contain information about the geometry, about material properties, about the loading, etc., etc. And it's not necessarily an explicit function. It could be just a computer model. The aim of reliability analysis is to estimate the probability of failure of this system. So we want to estimate the probability that the demand exceeds the capacity of this system. So we define this critical threshold y star, and we will say that the system fails if, when we evaluate our performance function G, the output is greater than this threshold y star. So naturally, the failure domain can be defined as the set of all inputs such that our performance exceeds that threshold. And the engineering reliability problem is formulated as computing the probability of failure. So our systems are so complex, there are so many unknowns, that our inputs there are modeled probabilistically to take into account all these unknowns. So the probability of failure is calculating the probability that the input x belongs to the failure domain. So we have to integrate over that failure region, and this pi of x is the joint probability distribution of our inputs. Okay? So how do we solve this problem? This, of course, is a very high dimensional integral, so we cannot solve analytically, and we need to sample somehow. And what we do to solve this problem is subset simulation. So this is a technique developed by Ivan Au and Jim Beck in 2001 to simulate rare events and estimate small probabilities of failure, where simulating rare events means sampling from the failure domain. Okay? So the idea is that you want to sample from that set F, and you're going to express or find a decomposition that expresses our failure domain as contained in a nested sequence of sets. So being that the case, F1 is an event that is relatively frequent, so it's easy, or it's relatively easy to sample from it, to generate samples from F1. Okay? So given this sequence of events, since they are contained in each other, and what we want to calculate is the probability of F, which would be the same as calculating the probability of the intersection of all these sets, it's easy to show that the probability of F is just the product of these conditional probabilities. Okay? So we have here the probability of F1, but F1 is frequent, so it should be easy, relatively easy to estimate that probability, and then from there we start calculating each one of these conditional probabilities. Okay? So how does this work? Schematically, let's suppose that we start with our original input space, and then we generate a relatively small number of independent and identically distributed samples. So I'm going to denote them like this, where the subscript 0 means the 0 level, or the first level of our algorithm, and the superscript is denoting the number of the samples. So they are all distributed as the joint probability distribution pi of x, and once I generate these samples, I can evaluate them using the performance function. Yeah. So at this first stage, it's going to be very, very unlikely that any of these samples falls within my failure region. Yeah, but I can evaluate all of them using my performance function, and I can rank them, I can order them, because I'm interested that some of these exceed the failure threshold. Okay, so I do the ranking, and then I choose a number p between 0 and 1, such that the number of samples times p is a natural number. Now, we can always define the first intermediate failure domain as taking the NP and the NP plus 1 sample that are ranked, and calculating the midpoint between those two. That number is going to be our first intermediate failure domain, and that will help us define our first intermediate failure domain. Okay, so let's say that we started by generating 1,000 samples, and p is 0.1, so we just keep 100 here. Okay. By construction, these NP samples are going to belong to the first intermediate failure domain, and the rest are not. Okay. So what we can do is use those NP samples and estimate the probability of this first intermediate failure domain. So we just add this indicator function, whether the sample belongs or not to the first failure domain. So this is zeros and ones, and we divide by the number of samples, and that gives us a first rough estimation of the of our failure domain. Okay, since our failure domain F is contained in F1, the failure probability can be written as this product here. Now, we have already estimated this via Monte Carlo. Our task has been reduced. Now we have to calculate the probability of F given F1. Okay, so the next stage, what we need to do now is to populate F1, having discarded the rest of the input space. Okay, so the samples are just going to belong now to F1. And the way we populate this intermediate failure domain is using a Markov chain Monte Carlo scheme. So we start with these NP samples that are seeds that we're going to use to grow these Markov chains and generate the rest of the samples needed. Okay, and you can imagine what's going to happen now. Once we have NP samples, N samples here, we're going to rank them again. We're going to generate or we're going to calculate the second intermediate failure domain, and we're going to populate that domain using our Markov chain Monte Carlo scheme, and we will continue doing that iteratively. Okay, so schematically, this is what's happening. By construction, these NP samples belong to F2, and then we use our Markov chain Monte Carlo scheme to populate F2, and we keep getting closer and closer to our failure domain. Okay. So so again, this is just a repetition of what I just said. Our task here is now to calculate the probability of the failure domain given F2. Okay. We continue doing this iteratively until some stopping condition. The scheme that we use to generate these samples is called the modified metropolis algorithm. So this was the original algorithm when it was published back in 2001, and it's basically a metropolis algorithm, but applied component-wise. Okay, so you take the first coordinate of your sample, and then you have a proposal distribution, let's say a Gaussian, because we want this to be symmetrical, and we generate certain realization with certain probability. We accept or reject, and then whatever has happened here, we change or we keep the same coordinate here, and we do that for all the coordinates. We test whether it belongs to the current failure domain, and if it does, we accept it, and if not, we reject it. Okay, so that's what's happening here. The stopping criterion, we continue doing that until what should happen? Well, if you concentrate in, say, the Lth intermediate failure level, we know that the number of failure samples that we have generated till then is just the sum of this indicator function. Now, the number of failure samples at the beginning is going to be very small, or it's going to be 0 for many levels. Yeah? It's going to be unlikely that we hit that target in the first levels. And in general, as we advance, we will be getting more and more samples that by chance belong to our failure region. Now, I've said that you can calculate this intermediate conditional probabilities using Monte Carlo. So, so every time by construction, this estimate is going to be equal to P, which is that number that we chose at the beginning. And so the probability of failure is P to the Lth, which is the number of levels so far, times this conditional probability. And the last term can be as well estimated just by counting how many of our samples are in the failure region divided by the number of samples that we have generated. And we just apply the following test. If the number of failure levels is greater or equal than n times p, which needs to be a natural number, then the current conditional level becomes the last one, and we can calculate our estimate for the probability of failure. And if not, if we still don't have p times n failure samples, then we go for another level. Okay. So this is an example taken from a paper by Williamson and Vernon. They have this this example of these domains. We are interested in sampling from the domain that is nested or that is containing all the other subsets, and using subset simulation we can populate that that set that is containing all the others. Now, so coming back to history matching, I said that implausibility is defined as this function here, and we are interested in sampling from the non-implausible space. So there is this condition that the implausibility has to be less or equal than a certain threshold. And this non-implausible space reduces very dramatically as our history matching progresses. So this is, the analogy here is, let's treat this non-implausible region as a failure domain, okay? So if we treat it as a failure domain, then we can use subset simulation to sample from this non-implausible space at each iteration of history matching when this non-implausible space is very, very small, okay? So this is what we have done, and we started testing this. I generally work with engineers, so so we have tested this with different models. This is a very simple analytical model. It's not even an expensive model. This is just to test the results, and this model is quantifying the weight of a light aircraft, and you can see here the different parameters of the model: the wing area, weight of fuel into the wing, aspect ratio. It even has a variable that quantifies for the weight of the paint. Okay, and what we do here is we have this model. We pretend we have certain observation. We want to achieve certain weight for that aircraft, plus minus certain tolerance, and using this scheme of history matching with subset simulation, we can have an idea of what is the non-implausible space after several iterations, after several waves. So you know, it's a 10-dimensional model, so I cannot show you any graph, but I can show the pairs of inputs, and you can see how. So, for example, the combination of these two inputs, this area of the input space has been discarded. Going to a more realistic application, was to with a problem, because we organized this study group with industry last year in Liverpool, and they came with this uncertainty quantification challenge, and it has to do with robust design. So they said, look, we have this simulator with a configuration space that is huge, and this configuration space measures characteristics of our aircraft, such as characteristics of the engine or of the geometry of the aircraft, etc. And we don't have time just to evaluate all of them, and we have certain design criteria. So what we did is we thought of this as analogous to calibrating a model. In history matching, you will have an experimental observation plus minus experimental error. In this case, you have certain design objective plus minus a tolerance. So we can treat this analogously, and we can apply history matching to solve or to get some insight in which is the non-implausible design space. The inputs for this model are variables such as fan pressure ratio, thrust, wing area, wing aspect ratio. So some of them have to do with the geometry of the aircraft. Some of them have to do with the engine capabilities. And what they were interested in achieving, or the outputs, have to do with emissions. We have to do with noise. Okay, so these are the four outputs of the computer model, and they were interested in designing this aircraft such that you can have, for example, a tolerable level of emissions, a tolerable level of noise. They came and spoke to us about what is an acceptable level of emissions, for example, and they came up with a value for that and a tolerance for that. We applied this history matching procedure using subset simulation, and again, after a certain number of waves, we ended up with a certain non-implausible space which can guide them in deciding which are the combinations of parameters that can achieve those design targets. This is for a single output, but they were also interested in testing the model with all of their outputs. And in that case, we need to define an implausibility that takes into account those 4 outputs. Okay, so we have provided these results, and aerospace engineers have looked at them, and it's very interesting to see how, well, for me this model is basically a black box, but for them, you know, with their expertise, with their expert knowledge, they are able to draw some insight of what this combination of variables mean for their design. Okay, to finish, I want to say something about some authors consider history matching not strictly as a calibration methodology. Some authors say that history matching is a pre-calibration methodology that will help you narrow the input space, and then from there you could, for example, do Bayesian calibration and obtain some probabilistic statements about your input space. Now, as I said before, the implausibility measure is defined as the distance between our experimental observation and the mean of our emulator. When it is possible to use emulators to approximate the output of an expensive computer model, because it's not always the case. I've seen examples in the literature for climate models, for example, in which this is not possible, so people resort to using linear Bayes. So Michael Goldstein, Ian Vernon, they use this other methodology that does not use probability as a primitive, but expected values to compute approximations. But when it is possible to use a Gaussian process to approximate the output, what we can do is that instead of defining implausibility as the distance between an experimental measurement and the mean of our emulator, we could define this random variable, which is given here by the output of the Gaussian process. So this is not a pointwise estimation of implausibility. This is a random variable that allows us to make statements or ask for statements as what is the probability of the implausibility being less or equal than 3. And this is somewhat related to what people do in Bayesian optimization. Yeah? In Bayesian optimization, you are interested in selecting a point that will give you the maximum information to run then again your emulator and reapproximate. So we are using this, or we are exploring this now, using this full probabilistic version of implausibility, and we are using measures such as expected improvement or this entropy profiling to decide where is best to select the next sample within the non-implausible space in the next iteration. So when we do this, here's a comparison of what happens. This is the pointwise implausibility function that I presented before. So the target is given by these solid lines. Those are the level sets, and our emulator at this stage is giving us this approximation given by the pointed lines. Black here means highly implausible, and what we see here as a difference between using this pointwise implausibility and this random variable for implausibility is that we have what I think is a better trade-off between exploration and exploitation. Yeah. So so when we use the whole output of the Gaussian process, then our prediction is more conservative, but that also gives us the opportunity to explore the space a bit more, because, for example, you see here that this is identifying this area here as with high implausibility, whereas here it still gives a chance to our algorithm for exploring these subsets of the input space. So this is something that I would like to develop further, and during this month that I will stay in Cambridge, I will be working on this. So as a conclusion, history matching is a form of calibration. Some people call it pre-calibration, that finds a possibly empty subset in the input space that provides a match between output and observed data. And there's a natural analogy between this non-implausible space and a failure set. So subset simulation is a way to solve the problem of sampling from this non-implausible space. Things that can be improved and things that can be researched on are the computational cost of subset simulation, because of course subset simulation also requires the constant evaluation of the computer model. So we could also use an emulator for that, but we would have to take into account the uncertainty that stems from doing that approximation. So there are several ways of doing this, but we're working on a new direction on this topic. I presented the modified Metropolis algorithm, but there are different ways of doing this. So we are also working on different versions of this algorithm. The problem, of course, is working in higher dimensions. The sampling there can be very challenging. And we are also interested in quantifying additional sources of uncertainty. So I spoke about model discrepancy, etc. But very recently, people are working on quantifying uncertainty that stems from computation itself. They call this probabilistic numerics. And of course, when we evaluate the performance function, we are really evaluating a computer model that will have model discrepancy, but will also have certain error that stems from the finite precision of our computer, for example. Okay, so these are things that I would like to discuss with you during this week and during this month, and I would be very interested in knowing your opinion. These are some references. It's not an exhaustive list. Thank you very, very much.
Okay, we did start a couple of minutes late, so I think we could take 1 or 2 minutes for questions if anybody has any. Michael?
So thank you, that was very interesting. So when I do history matching, let's say I do it through the emulator, and one of the key things is that some of the outputs I can't emulate initially, but later on I do. So the outputs that I'm matching in each way will be different, because I try to reduce dimension, so I look at my active variables, things that are active initially, I kind of control for them, and so my input space, sort of what was an input that was important in an early wave may not even appear in my equations for sort of several sort of things down the line. So I'm getting, so it's not clear to me exactly how nested all these things are as I go through waves. I mean, it's quite natural to do it, but the question about the structure, so I wonder how flexible your methods are for dealing with things like that.
Yeah, no, I'm very aware of, you know, I've read the work that you've done, that you, when you have your emulator and you concentrate very much on the term that takes, that models the global response, and you use different polynomials, different orders of polynomials. So in particular for the models that I have worked with, I've tried to apply that what you have proposed, and but I have not been able to reduce the dimensionality of the models. Or if I do some sensitivity analysis, at least for these models, these engineering models, I haven't found that there are variables that are more important than others. So far I have used the, all the dimensions, and in that case, it works this way. I wouldn't be sure what would be the effect of using for some waves using some variables, and then in the subsequent waves including them.
It's always a bundle of uncertainty for the things you've left out, but it's just an order of magnitude thing that pulls more stuff back in again.
Yeah, and it is true that, I mean, in every wave you will have to sample from that non-implausible space. So you will have, at every wave you will, following this scheme, you would have to, given a wave, apply, for example, subset simulation to do this. And you will have to do that every time. I don't know if this can be done independently, if sometimes you add or sometimes you subtract variables, but yeah, I'm afraid I don't have a complete answer for that.
Hard problem.
Yeah, it is.
One more quick question from Serge.
Yes, so how do you view history matching? More as a pre-calibration or as an alternative to calibration? How would you combine these two tools optimally if you were to be able to do that? Because I struggle myself with this.
Yeah, no, that's also a very good question. I'm inclined to think that it is also a pre-calibration, that it will give you some insight into which is the input space that you should be considering, and then if you want to apply Bayesian calibration within that reduced space, then you will be able to make some probabilistic statements about it. But
where do you stop? Is it a question of
do
you waste your
I think it's problem dependent, because also subset simulation is designed to sample from very, very small volumes. But at the beginning you might not have this problem. So at the beginning you might be able to sample just from a multivariate normal, and you won't have any problem. But maybe you can use measures like, you can track the variance of your emulator and see whether this is shrinking, and you say, okay, so this means that I'm getting a very, very small input space and my emulator is becoming more and more precise. So maybe there's a way to link that and say, okay, after certain tolerance for the variance of my emulator, I will start using something like this.
Okay, in the interest of time, I think we should put it off there and thank Alex again.
Thank you very much.